terrorism, instability, inequality, disease. There's one issue that will define the contours of this century more dramatic than any other, and that is the urgent and growing threat of a changing climate.
We were tasked with designing a small wind turbine to be tested in the Donald Campbell Wind Tunnel at Imperial College London. The target was to maximize the power coefficient to weight ratio, all the while maintaining self-start capabilities. Due to the wind tunnel size and testing equipment, several design restrictions were imposed on the project. Firstly, the wind turbine was to rotate clockwise on a horizontal axis, and maximum power should be achieved below an angular velocity of 3,000 RPM. Furthermore, the mass of the assembled structure should not exceed 500 grams. And finally, there should be between 1 and 3 blades, with an overall diameter not exceeding 500 millimeters. With these restrictions in mind, we began our design process, drawing on all our knowledge from aerodynamics, mechanics, and structural design.
To select our airfoils, we had to consider the length of our turbine and the lift-generating capabilities of the airfoil. To maximize the power output, we wanted to achieve the highest possible LOD ratio without compromising the structural integrity. As the forces along the blade's radius vary significantly, we decided to adapt the airfoil selection as required. SG6043 was chosen for its high LOD ratio and the coefficient of lift. However, near to the nose cone, the blade experiences high forces as it supports the rest of the blade and its moments, and thus requires a secret airfoil to ensure that the blade is structurally sound. In this aspect, S833 fulfills this criteria while still having good aerodynamic properties, albeit providing lower lift than SG6043. To ensure structural integrity without compromising lift to a large extent, airfoil S833 was used from the root up to 60 mm of the blade, while airfoil SG6043 made up the rest of the blade.
In order to find the optimal chord length for the turbine, the Betz and Schmitz equations were considered. From theory, it is given that the optimal chord length is proportional to 1 over r. However, to find the exact relationship between these, the planform area of the blade is considered. We compared the Betz and Schmitz equations, and ultimately based our chord lengths on the Schmitz equations, as these account for whirlpool losses and thus provide a more accurate estimate. After having calculated the chord lengths, manual adjustments were made near the hub to create the least amount of drag with the best structural stability.
TSR was initially estimated to be 4.2 based on existing literature for small turbines. The chord lengths were then calculated at each interval using Smith's equation and entered into Q-blade together with the twist and airfoil types. We then ran simulations on Q-blade to obtain the CP and estimated power output for each case. The chord lengths were then recalculated for different TSRs and used to predict the optimum TSR, which would yield the highest power output for our blade. After having repeated the process for a range of TSRs, the optimum TSR for our blade was decided to be 4.8. Although higher TSRs were predicted to give a higher CP, the maximum rotation speed was taken into consideration in the selection process.
As we move along the turbine's radius,
the tangential velocity of the blade increases,
and the relative wind speed changes. In order to keep the blade at its optimal angle of attack to generate the maximum lift, a twist angle is applied. Using a formula to calculate the twist angle, we wrote a MATLAB code which would overwrite the airfoil coordinate data file of our chosen airfoil to account for the twist angle.
There are 3 considerations in designing the nose cone, namely to reduce air drag, to minimize the weight, and to maintain structural integrity. The nose cone is designed based on a calculator found in the Rocket Forum. After specifying a few parameters, such as cone length and root diameter, the calculator was able to generate the x and y coordinates of the outline of a nose cone, which could then be imported into Creo parametric. An ogive nose cone was designed to reduce air drag, and its front part was made hollow to minimize the weight. In addition, the root part of the blade was merged with the nose cone, and the structure was made into one piece using 3D printing technique.
For manufacturing, the hub was manufactured in the workshop using a series of processes, while the blades were manufactured using a rapid prototyping machine. To manufacture the hub, A cylindrical piece of aluminium was put through turning, drilling, milling, threading, and broaching in the order specified. Firstly, by using a lathe, a single point cutting tool was used to reduce the diameter of the cylindrical block to the required dimension of the hub. Using the same machine, the tailstock is then used to drill a hole in the center of the block so the hub can fit onto the test rig. The cylindrical block is then put through a milling machine and cut to the desired shape. The milling process is used to produce prismatic surfaces that the hub design encompasses and is effective as it works based on the 3 orthogonal axes, disregarding the cylindrical surface. For the same reason, the milling machine is used to drill the holes required by the design on all 6 surfaces of the hub. To accommodate the grub screw, a threaded hole is required in the hub, and this is done by putting a tapping drill through the hub using a tap wrench. Finally, the keyway for the hub is created by using a broach, which is basically a multi-pointed cutting tool. The broach is then pushed through the hub by using a hydraulic press to create a keyway.
The two ways of joining the components are glue-in, requires a large surface area, or a self-locking joint, which will create higher stress concentration. Our final design is a hybrid finger and dovetail joint near the thickest section of the blades.
Once the general design was complete, we needed to verify that our turbine was structurally sound. 2 failure modes were studied in particular. The first one was longitudinal fracture of the blade due to centrifugal forces. A MATLAB script was written to calculate these forces. The second failure mode was perpendicular fracture of the blade due to aerodynamic forces. Once again, a MATLAB script was written to calculate these forces. Finally, we wrote a third MATLAB script to compile all these forces and verify that the structural integrity of our turbine would be maintained throughout the testing.
The blades and nose cone in the turbine are manufactured using a rapid prototyping process known as fusion deposition modeling. This method is used as it is good for producing rigid functional models from ABS plastic, which can be machined, sanded, and tested. Due to the size restrictions of the rapid prototyping machine, the nose cone and blades were printed separately and thus need to be glued together. The wind turbine was glued and allowed to settle for a day before sanding took place. In the design stage, the turbine was designed to be thicker than desired, and sanding is used to reduce the thickness to the required dimensions. The surface of the blade was also sanded to create a smooth surface and for better aerodynamics.
From our test, we found that our CP max is 0.124 and our RTSR at max CP is 5.94. From the CP plots, we found that our turbine is generally good at low speeds, so around 6 to 8 meters per second, and it will store at higher speeds above 10 due to the over-optimized blade profile. Though we were able to get very low blockage, the power output was relatively low. Therefore, to maximize power, we had to twist the blade in accordance to the alpha L/D max of the airfoil section facing the local velocity. In doing so, coupled with the nature of the main airfoil section, SG6043, having a sharp lift-drag curve caused large performance drop-off away from the optimum RPM, thus explaining the power spikes we saw on the power RPM graph. The limited range of performance is also reflected in quite aggressive stall cycle behavior beyond this range. We speculate that the thin SG6043 airfoil may have suffered thin airfoil stall, especially near the blade tip, where the manufacturing was proportionally less precise, thereby the leading edge was too sharp. This, along with the thin blade profile and optimization for high RPM, meant the angle of attack was too high to produce torque in low speed conditions. As a result, the self-starting speed of the turbine is quite high. It was also immensely difficult to blend airfoil sections together, as the aerodynamic behavior of the localized section and the blending section as a whole cannot be predicted without modeling in CFD, which is expensive in terms of cost and time. Therefore, an unquantified approach to blending was taken, resulting in a bump on the pressure side of the medial blade section. During the initial test, we predicted that the bump had increased drag. Our theory was supported by the retest. When the bump was removed, the performance of the wind turbine improved. Interestingly, with the removal of the bump, the self-starting speed increased.
Overall, this project has been a great learning experience, combining all aspects from our course in one project. Our turbine was designed for high speeds while maintaining a very low weight. While we were able to achieve a total mass under 100 grams, the turbine stalled at higher wind speeds. We were able to extend the operating envelope by making some modifications to the geometry, which yielded a comparatively high merit function. To bring the turbine to practical applications, a general focus should be put on extending the stable operational envelope, both to lower and higher wind speeds, depending on the application. Based on the average UK wind speed of 4.5 meters per second at 10 meters height, the design may be easily adapted for small-scale private deployment.